Our next two videos we're going to talk about interference. And the first part we're going to have an interference with two sound sources with the same frequency. So that's going to be our discussion in this video. And the next video we'll talk about interference due to two sound sources with different but close frequencies. And we'll discuss that it's also called beat. So let's look at the interference with two sound sources with the same frequency. So here's a representation. We have speaker A and speaker B. They're separated by some distance d. So we want to remember that, start my pen here, that each speaker produces the same frequency. And these circular lines here, these curves, they are showing where the amplitude or the trough, the crest or the trough of the waves coming out of the speaker. Now you notice that where these points meet, we're having constructive interference, meaning that it's doubling in size. If we consider these to be the same amplitude, it would be a double. And notice that these lines pretty well line up with each other. I just can't draw straight with this pen, sorry about that. But these points are drawn along a line for our constructive interference. Now, points in the middle that are in between the two, this would be destructive interference. And notice that these also exist on a line in between the constructive interference. So the points of constructive interference, where I'm getting double of the amplitude, happen at multiple wavelengths. So here's a wavelength, here's a wavelength, right here, and a wavelength, right? So this is where we get our constructive interference whenever these points are on multiple wavelengths of each other. Now, for the center, it's equidistant to the amplitudes on both sides, and so this would be in between. That would be 1/2 lambda. So we can say that we have constructive interference at, can't spell, at multiples of lambda, and we have destructive interference well, I have to go multiples of lambda plus 1/2 lambda. So at multiples of lambda plus 1/2 lambda. So the multiples are just getting you out further, and then the 1/2 you're just going to add to that multiple. And these are going to be the locations of destructive interference. Now we can show this in a simulation. You notice that here I have two sources. They're 0.3 apart, say 0.3 centimeters apart. And as you play the simulation, you can see these areas of destructive interference going out in these straight lines, and the white would be the constructive interference. So this is why you never find a theater with exactly two speakers separated in the audience, because there will always be areas of destructive interference, places where the sound is going to be terrible, and then you're going to have places where the sound is incredibly loud for people in those sections. Another interesting thing is what happens if we take the waves out of sync 180 degrees. Notice that it's just replaced our destructive interference with constructive interference. It's just shifted. So watch this center line. It'll help you to be able to see when I switch it back. Right now this center line is destructive interference, and now it's constructive interference. Now we can separate our sources, and it's just going to add more areas of constructive and destructive interference by separating them. If we put them very close, notice that my amount of destructive interference is larger, but less number of them. And let me put it even closer. Now it just looks like one source when they're that close. So this is the idea of interference of two sources with the same frequency, providing you constructive and destructive interference. And this is what it would look like if you could see the waves moving in time.